Hello everyone, Jai Gurudev. My name is Sakshi and I am doing my PhD in nuclear and particle physics. I just had the very great and blessed opportunity to show my work to Gurudev, and he asked me to present it to you all, so I thank him for this opportunity. So today I'm going to give you a glimpse of some of my work, and I am waiting for it to get displayed onto the screen, but okay, there we are. So I will talk a little bit about exploring the unknown territories of antimatter and quantum physics. You might have heard Gurudev say about quantum physics every now and then, so it's a very exciting field. So to begin with, before we dive deep into the antimatter, I would like to give you a brief introduction about matter. So can we go to the next slide, please? Okay, so this is the periodic table of elements. Many of us might remember this from our chemistry school class. So the table of elements that you see here, it just shows 118 elements. So I'll tell you about, they can be divided into two categories. So one category is that all these elements have a stable form of them. And the second one is that they have unstable form, which we call radioactive elements. So these stable forms are only 118 in number, but the unstable ones, or the radioactive, that are produced and made in the laboratories for nuclear and particle physics, that's about 3,000 in number. So next slide, please. Talking about the elements, so you know when Big Bang happened, that time there was only hydrogen and gravity playing all the role. So the chain reaction started happening, and you know the heavier elements started building up, and it went all the way up to iron element you might have heard of. So that is the most stable element, natural element that exists in the universe. And beyond that, there is no chain reaction. So one of the biggest unanswered questions in physics, that is also in Discover magazine, is that how did the heavy elements from iron and up to uranium, which is the heaviest element, how did it come into being? How was it made? So I was going to ask you to raise your hand to give an answer, but I think we are running short of time, so I will skip that part and jump to the answer. Next slide, please. Okay, so the answer lies in the famous quotation you might have seen from Carl Sagan, who is a big astrophysicist. He says that we are all made up of star stuff. And that is really true. You know, as a child, I used to wonder that, what star is right up there? How can it make me? But that is true. And how that is true is that, you know, all the galaxies, us, even the pizza that we eat, or the DNA in our body, that is all made up of atoms. And if we want to understand the life, how it presents itself, we need to know the atoms that were formed in all the astrophysics processes, and that is all linked. If we can learn about those atoms, we can learn about everything that exists and does not exist. And there I am talking about dark energy and dark matter. So, like we have a thumbprint, you know, which is very unique to us, it's exactly the same way all these elements have a unique mass, each atom of a particular element. And if we can learn about their masses very precisely, we can learn about all their physical and chemical properties. Next slide, please. Okay, so now I'm going to talk about a very interesting thing. I am doing my research at Triumph, as I told you. It has world's largest cyclotron. You might have heard about this term from CERN, which is another very interesting particle accelerator center in Switzerland. So this cyclotron is able to speed up the speed of the particles to 75% speed of light. And to give you a context of it, if I were to go with that speed from Earth to Moon and come back to Earth, it'll just take me 4 seconds. So that is the speed with which we accelerate the particles, and then they are bombarded onto a nuclear target where the nuclear reactions take place, and all sorts of radioactive nuclei are produced, which we use to do our experiments. Next slide, please. Okay, so coming to the mass measurements, as I talked so much about masses, how we are doing it at the lab using a device called penning trap. On the left, you can see, in simple terms, it's just a weighing machine. It's going to weigh the mass, but on the right-hand side, what you see is the real penning trap, and this weighing machine, as I like to call it, is so precise that it is able to measure the mass of a single nucleus of an atom. A nucleus which we cannot even see. It is so tiny, and this device is able to measure the mass. Next slide, please. Okay, so you must be wondering that why do we want to measure the masses beyond just one certain application? So there are many, many applications of this work, but to name a few, this work, so with the masses, we can know more about the nuclear structure and astrophysics. I'll say a fun fact about the nucleus. Why do we want to learn more about nuclear structure? The nucleus in an atom, it's so tiny that it is just, 1 divided by 1 lakh times smaller than even atom itself. So as Gurudev says that 99% of atom is also empty, indeed that is true. So other than that, the application is in medical physics as well. So we prepare and develop isotopes that can treat cancer. And then we find penning trap technology into quantum computers as well. And very, very interesting application goes into fundamental symmetries, which I will talk on the next slide, please. So now I will tell you a little story about asymmetry between matter and antimatter. So as Big Bang theory says that, when this universe was created, there was matter and antimatter in equal amounts. But what is antimatter? So all the matter that we see around, every matter particle has an antiparticle. But what's the difference? They both have same masses, but the charge that they have is different. So if one is positive, the other will be negative. And when they both... All right. Okay, I thought you just... was that a cue to stop? Okay, I will be very quick. So the research that I am doing is the recent experiment that I did at the laboratory at Triumph that was with a particular radioactive calcium. And with that, we'll be able to understand more about the particle and antiparticle and antimatter story. So if, the results are still on wait with the data analysis, so if that comes around, okay, it will be solving this big puzzle of what antimatter is. And I will quickly jump to the last slide, where I want to speak a little bit about vacuum. Can you change? Okay, here. So vacuum, you must have heard about vacuum cleaner, that if we clean it, then that space should be empty, and that is what vacuum means. But really, vacuum is not empty. It has quantum field in it, and what we say as matter, it is excitation, the quantum fluctuations in the field. So how I love to relate that with is when Gurudev talks about Shiva Tattva, which is the universal energy, which is everywhere, and we, all the matter that comes around, is just that fluctuation in the big energy field. So thanks to Gurudev, who introduces all this infinity within us so beautifully and easily. And thank you, everyone, for your attention. I'll be hanging around in the ashram for a couple more weeks. If you have any physics questions, please feel free. Thank you.